Hello and welcome to Data Analysis and Visualization. I'm Jivita Christie, and in this video, I'm going to explain to you inference in statistics, and we are going to see two different forms of inference. So let's begin. Here we are going to introduce three forms of statistical inference, and there are actually three, but in this video, I'll be covering two. And each form is going to represent a different way of using information obtained in the sample to draw conclusions about the population. So these forms are number one, point estimation, number two, interval estimation, and number three, hypothesis testing. And in this video, we are going to talk about point estimation and interval estimation. And in the next video, I'll talk about hypothesis testing. So what is point estimation? In point estimation, we estimate an unknown parameter using a single number that is calculated from the sample data. So this is just a sort of a definition of point estimation, that you have an unknown parameter which you will calculate based on a single number that you got from sample data, which we have already done so far. So example of this is based on sample results, we want to estimate that P, the proportion of all US adults who are in favor of a stricter gun control, which is 0.6. So we found this data based on just a sample. A sample is a proportion of US adults. We are not talking about everybody. We're just talking about a small proportion of those. And we found out that based on their opinions, they are 0.6. They are 60% in favor of a stricter gun control. So this is point estimation, an example, and we'll see a little bit in more detail about it a bit later on in the video. The next thing we have is interval estimation. So in interval estimation, we estimate an unknown parameter using an interval of values that is likely to contain the true value of the parameter, and also state how confident we are in that interval, which indeed captures the true value of the parameter. So interval estimation not just gives you one point or one value, it gives you that one value, but along with that, it also gives you an interval which specifies that this is what we got from the sample, but this is the interval in which the value of the entire population is going to fall. So it is sort of an estimation of how much error can be there if you apply whatever you did on the sample population on the actual population. So that is interval estimation. And along with all this, interval estimation also provides some sort of a confidence value with it. An example of interval estimation is based on our sample results. We are 95% confident that P, which is proportion of US adults who are in favor of stricter gun control, is between 0.57 and 0.63. So based on what we got from the sample, we are giving a confidence value, as well as we are giving a range, an interval between which our original sample can fall, between which our original population can fall. So this is interval estimation. The third form of inference is known as hypothesis testing. So in hypothesis testing, we have some claim about the population and we check whether or not the data obtained from the sample provide evidence against this claim. So this is all about having some claims and then proving whether or not those claims are correct based on some evidence or some data which we have about the sample that we have taken from the original population. And this is known as hypothesis testing. We are not going to be discussing this very much in detail in this video because I'll talk about it in my next one. However, we are going to go through a small example of this. So let's take an example. It was claimed that among all US adults, about half are in favor of stricter gun control and about half are against it. And in a recent poll of a random sample of 1,200 US adults, 60% were in favor of stricter gun control. This data therefore provides some evidence against the claim. So there was a claim that 50% of people are supporting gun control, a stricter gun control, and the remaining 50 are against it. Now that's the claim that we want to test. And to test it, we are given the data that there was a random sample of 1,200 US adults taken from where 60% were found to favor a stricter gun control. So this data now provides us some sort of an evidence against the claim, and we can talk more about a claim, or we can say that the claim is more true or more false based on this extra evidence that we have. So this is an example of hypothesis testing. And let's take a look at one more. So it is claimed that among drivers, who are 18 to 23 years of age, there is no relationship between drunk driving and gender. A roadside survey collected data from a random sample of 5,000 drivers and recorded their gender and whether they were drunk. The collected data showed roughly the same percent of drunk drivers among males and among females. These data therefore do not give us any reason to reject the claim that drunk driving is not related to gender. So hypothesis testing here works because we are talking about drivers between the age of 18 and 23. Between this age, we are trying to make a claim that there is no relationship between drunk driving and the gender, just for drivers who are 18 to 23 years old. Now, to prove this claim, either true or false, we made a roadside survey where we took a random sample of 5,000 drivers and then we recorded their gender and tried to find whether they were drunk or not. So this collected data would show us roughly the same percentage of drunk drivers between males and females. So because this was the result of the sample, we can conclude that probably the claim that we made might also be true. So this is again an example of hypothesis testing. Now let's talk about inference for one variable. When we are talking about inference for one variable, if that variable of interest is categorical, then the population parameter that we will infer about is the population proportion P associated with that variable. So for example, if we are interested in studying opinions about the death penalty among US adults, then our variable of interest is death penalty, which is going to be whether people are in favor or against, which is a categorical variable and not a quantitative variable. And therefore, we will choose our sample of US adults and use the collected data to make an inference about the proportion P of US adults who support the death penalty. So what about quantitative variables? If we are talking about quantitative variables, so if the variable is quantitative, then the population parameter that we infer about is the population mean, which is denoted by mu, that is associated with that variable. Let's see that also with an example. If we are interested in studying the annual salaries in the population of teachers in a certain state, we'll choose a sample from the population and then use the collected salary data to make an inference about mu, which is the mean annual salary of all the teachers in that state. So notice how when it's a quantitative variable, we are taking the annual salary, the average annual salary, and comparing it with whatever result we get. But when we talk about categorical variable, we cannot take an average. And that's why we compare our sample result with a proportion P of the population. And that is how we make inference. Next, let's talk about point estimation. So point estimation is the form of statistical inference in which, based on the sample data, we estimate the unknown parameter of interest using a single value, and hence it is known as point estimation. And of course, I talked about this earlier too. Now, point estimation, we are going to see an example. So suppose we are interested in studying the IQ levels of students at a university called Smart University. Then in particular, we want to study this variable, and we are interested in estimating mu, which is the mean IQ level of all the students at this Smart University. Now, because IQ level is a quantitative variable, because it specifies quantity and not a category, that's why we are talking about mu in this case. A random sample of 100 students of this university was chosen, and then their sample mean IQ level was found to be x equal to bar x equal to 115, which is their mean. This is the mean of 100 students. Because our sample is limited to 100 students, so we cannot perform on the entire student body. That's not possible. So now if we wanted to estimate this, if we wanted to estimate mu, the population mean IQ level by a single number based on the sample, it would make intuitive sense to use the corresponding quantity in the sample, which is bar x equal to 115. So we say that 115 is the point estimate for mu, and in general, we'll always use bar x. And here you can see a diagram depicting the same thing, that whatever you found data which is for your sample, you are trying to also use it for the entire population. So whatever is the average here is the same that you'll be using for your entire population. That is what point estimation is all about. Now, next we are going to see what is the problem. So point estimation is simple and intuitive, but it's also a bit problematic, and here is why. When we estimate, say, mu by the sample mean bar x, we are almost guaranteed to make some kind of error. Even though we know that the values of bar x fall around mu, it is very unlikely that the value of bar x will fall exactly at mu, which is obvious because you are only analyzing a sample. You are not analyzing the entire population. So it's not enough to say that this is the mean of the sample, because if you just say that this is the mean of the sample, it's possible that the population's mean is not the same. It will fall somewhere around that, but we do not know how much error is going to be there. Given that such errors are a fact of life for point estimates, by the mere fact that we are basing our estimate on only one sample, that is a small fraction of the population, these estimates are in themselves of limited usefulness unless we are able to quantify the extent of the estimation error. So what is important here is to know how much error would be there. How far or in what range will your actual population mean fall? That is what we want to know. And that's what we can come to know if we see our next type of estimation, which is interval estimation. So this issue is addressed by interval estimation, and the idea behind interval estimation is therefore to enhance the simple point estimates by supplying information about the size of the error attached. So now in interval estimation, we want to enhance whatever we found through point estimation by attaching how much error can happen by quantifying that error. So let's see an example. Once again, the same example that we are interested in studying the IQ levels of students at this university called Smart University. And in particular, we are interested in estimating meal, which is their average IQ level. So the mean IQ level of these students at Smart University. So we take a random sample of 100 students from this university, and um, we have chosen their mean IQ level, and we found their mean IQ level to be bar x equal to 115. And once again, the same diagram that we saw a little bit earlier. So same diagram is present here. Now, based on this diagram, based on this data, if we are which is in point estimation, when we said that bar x is equal to 115 as an estimate for mu, but we did not have any idea earlier what the estimation error was, which means this is my sample mean, but what about my population mean? How much error would be there in that? What is the possibility? What is the range? So interval estimation takes this point estimation a step further and says something like, I am 95% confident that by using the point estimate bar x equal to 115 to estimate mu, I am off by no more than 3 IQ points. So now the error is quantified by 3, and also the confidence is mentioned, that there is a confidence of 95%. In other words, you can say I'm 95% confident that mu is written within 3 of 115, or between 112, which is 115 minus 3, and 118, which is 115 plus 3. Now, the thing to note here is that while point estimation provided just one number as an estimate for mu, which is 115, interval estimation provides a whole interval of plausible values for mu between 112 and 118, and also attaches the level of our confidence that this interval indeed includes the value of mu to our estimation, which in our example was 95% confidence. So the interval 112 to 118 is therefore called a 95% confidence interval for mu. And that is what interval estimation is all about. And there are ways to calculate this error, to quantify this error, and also to calculate the confidence. But I'm not going to be covering it anytime soon in these videos. Later on, it could be covered in some sort of an extra video, because we are only going to look at this subject from a programming perspective and not a statistical perspective. So in my next video, I'll talk about hypothesis testing, which is another form of making inference, of making statistical inference. So I'll see you there, and thank you for watching.